Since I started this YouTube channel and presented my first videos on semiconductors, I was sort of amazed to find out that I had a lot of blowback. Well, all the currents are backwards. It doesn't flow from negative to positive. Let's look at this drawing right here. This is what I normally present today to keep people happy, because this is what they've been taught in college and so forth. And I recently got a sort of a nastygram from a visitor who saw one of my earlier videos when I used electron flow and not positive flow that you've been taught in college. So I'm going to address that here, and you need to know this stuff because you might get away with it with semiconductors. You can't get away with it with a lot of other electrical devices and scientific principles in general. Okay, here you go. 24 volts positive to negative. It is wrong. This is correct, and I'll show you why. It flows from negative through Q3, through the motor, back through Q1 to plus VCC. This is a drawing that compares bipolar transistors, IGBTs, and power MOSFETs. It comes from an engineering paper, and it's been put in several of them. And let's observe something here. This is an NPN transistor. This is a IGBT, and this is an N-channel MOSFET. Let's note some differences here. Here's your base, here's your emitter. Your emitter, of course, on an NPN is negative. Ooh, you notice something, that most of your current flow is from the negative emitter to the positive collector. Isn't that interesting? Here with an IGBT, and I'll address those on different videos, you notice that the emitter, which goes to the negative side or ground, most of the current flow is from negative to the positive collector again. Isn't that interesting? Go to a power MOSFET. N-channel, its source is negative, and all of the current is negative to positive. The drain is positive. Let's note something here. Transistors have what is called electron and hole flow. IGBTs have electron and hole flow. MOSFETs exclusively are electron flow. All right, I'm sure you're scratching your head like, what has this got to do with anything? I'll show you. For one thing, these are solid devices. These are not liquids and these are not gases. I'll cover that in separate videos. These are solid materials. Now, I'm not going to argue with them on quantum theory and holes, whatever, but I can tell you for a fact, in an electric wire, the only charges that are moving are electrons. Let's look closely at an N-channel MOSFET. Here is your source. You notice here's my gate voltage. It's going to be positive relative to the source connection. And up here, the negative terminal, the 24-volt battery, goes to the source through a load resistor to the drain. The gate is nothing but a thin metal layer, and you have an insulator between what is essentially P material. With no charge on the gate, there is no current flow possible under this setup, because if you go over here, this here forms a reverse bias diode, thus it will not conduct on this end. Now I'm going to close my switch. You notice that I put less than 20 volts. Most of the gate VGS, that's voltage gate source, should never exceed 20 volts on most devices. And this is a bleeder resistor to make sure it turns off when I open the switch. But when I apply a positive charge here, it will repel the What it does is it forms an N channel that allows the flow of electrons, just as the engineering sheet says. The only flow you have through here from source to drain, of course, is electrons. But look up here. Electrons are negatively charged. So you notice I have the arrow up here with a question mark. Your college textbooks and your professors will tell you the current is flowing from positive to negative. No, it is not. The only current flow through this device is negative to positive, and the only way to return charges through this device to complete your circuit is back through the positive and the load. That is how it really works. And it isn't just these devices that are going to give you problems. This is a MOSFET. Their own engineering says the only flow you have here is electron flow. I got news for you. Negative charges, electrons are attracted to the positive side. That's the law of physics. Typical is this headache that I ran into with my college textbooks. Now, Principles of Electric Circuits by Floyd. Floyd is a widely read author in community colleges, but you notice something here. In the fourth edition, around 1990, you notice that we have, in one edition, we have negative to positive. This is called electron flow. Yet in a different edition with the same figure, we have positive flow, or conventional flow as they call it. Let's look down here at the bottom. This is called a cathode ray tube. I should know how these work because I built one in high school. I won an award in the physics for it. All right, what you do is you take a glass tube, seal the ends, pump the air out, and apply a high voltage. And what you will get is the cathode, the negative side, will begin, the voltage is so high it will push electrons. The only charges that are moving here are electrons if you get all the air out, to the anode. So the current flow in a Crookes tube is cathode to anode, and it's electrons, just the same kind of electrons that you see in an N-channel MOSFET. All right, let's ask a question here, and let's look at something else. All right, one of the explanations I have for diodes and bipolar transistors, well, the arrow points in the direction of current flow. Well, not really. The arrows actually point to the N-type material. Take a look at these MOSFETs. The only current flow you're going to have is from source to drain and drain to source. Are these arrows pointing at the current flow? Really? Remember, source to drain current flow, but the arrow is pointing 90 degrees the wrong way. So, no, the arrow does not stand for pointing to the current flow. It points to the N-type material. In the case of an N-channel, it's going to point inward to the N-channel, N-type material. Since there is no N-type material other than that in the substrate area around it, with a P-channel, it will form a P-type material when conducting, and thus the arrow is going to point away from it. I hope that doesn't have your head spinning too much. The question is, how did this happen? Everybody, or at least Americans, should know who Ben Franklin is. He was famous for his experiments in electricity. But let's note something. In 1752, prior to electricity being identified with the electron, Ben Franklin chose a convention regarding the direction of current flow. Franklin assumed that positive charge carriers flowed from positive to negative terminals. We now know that this is incorrect. In metals, The charge carrier is the electron, whose charge is negative by definition. Note the negative sign, and it's minus 1.6 times 10 to the 19th coulombs. So the only charge that can move through a metal or solid conductor is an electron. Let's note this excerpt from nutsandvolts.com. That's the magazine that a lot of us should be familiar with. To quote Nuts and Volts, scientists, engineers, college professors, and others have known for over 100 years that current is really moving electrons. Yet they have continued to use the original positive and negative current flow model. This has come to be known as conventional current, CCF. Today, this concept is still widely used in almost all universities and still taught in science and engineering programs. It wasn't until the mid-20th century that electron flow was widely taught. This came about as a result of the massive training of electronic technicians during World War II. The Army and Navy decided that electron flow was more appropriate than conventional flow, so they developed all their classes and training materials using electron flow. After the war, electron flow caught on and became the primary way of teaching technicians in community college, technical institutes, and vocational schools. Why the scientific, engineering, and academic communities refused to change to electron flow is not known. I've speculated on myself for years of this. Let me tell you right now, my background is military. And electron flow, when you're actually working with a lot of diverse types of equipment, is the only thing that makes sense. You can fudge it if all you're dealing with is semiconductors and ignore a few things, but it doesn't work with a lot of other devices. It makes no sense to use conventional flow with many devices. These are vacuum tubes. This is the closest non-semiconductor device we have to a MOSFET. These, you could say, these are the direct ancestors of your MOSFETs. All right, what you usually have here with a vacuum tube is usually a glass metal envelope that has all the air pumped out. You have a cathode, which is connected to the negative of the power source. The plate, which is the anode, is connected to the positive terminal of a battery. These things are high voltage. They're still used in things like guitar amps and stuff, and they can have 300-400 volts on the plates. And they're a little more complex than this one, which is called a triode. The way we control the current is we have a control grid. As we change the negative charge on the grid, we can control the current flow from cathode to anode. The more negative the grid, the less current I get from cathode to anode. Connect an audio signal on here and put a load resistor out here and take your audio off of that. You have an audio amplifier. It can also be done with RF and so forth. Now, as typical, I found most of this drawing on the web. This was wrong, several other things was wrong, and I went and corrected it. But this is the only thing that can work. You get a cathode that is hot. It adds enough energy to the electrons in the metal cathode. The cathode, by the way, is coated with rare earth oxide, sometimes thorium, I think, to be better. It's called thermal emission. The electrons, if you don't have a positive charge on the plate and you just heat this up, the tube will fill essentially with floating electrons, which will, of course, the minute you apply a positive charge to the anode, you will get a current flow from plate to the positive terminal. All right, let's look at some vacuum tube diodes. Yes, your first practical diodes were vacuum tubes. They may have had something like selenium rectifiers, but those things were horrible. Here you again, this is a filament. All this filament and battery does is heat up the cathode to boil off free electrons. And of course, those free electrons are going to be attracted to the positive terminal. So it's from cathode to anode through the plate resistor on back to the positive of the power source. This is another version of it where the filament the filament is the cathode. This battery serves no other purpose than to heat up the cathode. Again, you're boiling electrons off into a vacuum. They are attracted to a positive plate, flow through the plate resistor back to the positive terminal of the battery. Now, what happens here is if I reverse the polarity, the plate is negative and the cathode is positive, I will get no current flow because the plate is cold where the negative terminal is, and I can't use any heat to boil electrons off to complete the current flow. So this is a diode. The cathode here corresponds with the cathode on your diode. The positive anode is the anode on your diode. Your current flow, in actuality, in a diode, is against the arrow. The arrow is merely pointing to the negative material. These work exactly the same, and the current flow is negative to positive, and we're going to discuss power supplies in a minute. Again, this is the very same thing, it just has a separate heater for the cathode. What you see here is the outline of a 5Y3. This is essentially a dual vacuum tube rectifier. I probably have replaced hundreds of these back when I was a teenager, when I was working mostly with vacuum tubes. Here is a typical power supply you will find for maybe a vacuum tube amplifier in a guitar amp. If you remember your basic, using the center tap transformer in this configuration, we're going to divide the 425 volts by 2, and then when rectified and filtered, it's 425 divided by 2 times 1.41. It's 300 volts approximately. All right. I didn't show the heater here in this particular rectifier. I did not show the heater, but it's there, as where the heater was the cathode in the 5Y3. But again, electrons are boiled off the cathode here and migrate to the plates. And your current is from cathodes to anodes. Notice the arrow. That is your real current flow. Okay, if you're blowing your mind right now, think of what happens here at the capacitor. I am not pushing positive charges onto the positive plate of the capacitor. Instead, what I'm doing is removing electrons from the positive plate, and through the ground setup, I'm adding electrons to the negative side of the electrolytic capacitor. That's how you charge a capacitor in reality, is you're not pushing positive charges onto the positive plate. You are removing negative charges, leaving behind a positive plate. Again, by removing electrons from the positive plate, I leave a positive charge on the plate, and of course electrons will be transferred to the negative plate through the center tap. Now let's draw the same full wave rectifier setup with diodes. You got them down here, anode to cathode, anode to cathode. Again, the same effect as before. And remember, diodes only conduct in one direction. So electrons are pulled from the positive side of the capacitor, but cannot return because the diodes only conduct in one direction. One student, for example, described a diode as a electric check valve, and it is. Current flows in one way and cannot come back. And the only way that you can really return this is either through the resistor or simply short out the capacitor. You'll discharge the capacitor only through the load. So both of these full wave rectifiers work the same way. I guarantee you, the only charges moving through these wires, the transformers, the wires, the connections, everything up here is electrons. You cannot move positive charges through a solid metal conductor, unless, of course, you vaporize the conductor and blow it up. Let's discuss another oldie from the past, the reel-to-reel movie projectors. Now, if you're under the age of probably 35, you're not likely to have seen one of these. How that you have film on a reel, and it has pictures. This goes through a set of cogs and gears, but on the film, interestingly enough, is your audio is encoded on the film as well. Now this, I think, was Dolby. The earlier older films had only a single mono track, and there's information encoded here. Nobody's using these anymore, but it's interesting to know how these worked, because because the same light that you shone through the film to produce a picture through the lens also shined through the audio tracks over here and fell on a photodetector, where they would be detected, amplified, and fed into your speaker system. What you're looking at here is a phototube. Again, it is a vacuum tube. It has a metal plate. You see the metal plate here, the back of it there. This is an actual phototube. I've actually had these in my hands before. They're interesting. The metal plate, you have light come in from this side. The metal plate is coated with cesium oxide or other materials that are called photoemissive. If struck by a photon, it knocks off an electron, and the electron floats around in the vacuum. By adding energy to various, be it thermal or photonic, to various materials, you can knock electrons off, and they'll be floating around in the vacuum. You will have this small wire. You see it here. It's on the other side of this. I wish the photo had turned it around. The free electrons are now attracted to the positive anode, and the current flows, of course. And of course, as electrons are knocked off the sensor plate, more will flow in through the negative, and the free electrons will be attracted to the positive. Here's a circuit over here. Here is your negative plate. This represents the curved plate. These are the free electrons knocked off by the photons. They are attracted to the positive anode and back to VCC. And depending on the intensity of the light shining through the film onto this phototube, you have your audio signal, blocking capacitor, and send it to an amplifier. So that's how your old reel-to-reel films had audio. Your earliest ones did not. It wasn't until they developed vacuum tube amplifiers, probably after the 1920s, did you really start to get audio on your films. So ends this brief lecture on electron current flow. Don't worry, from now on I'm going to use conventional current on anything that's solid state. I'll continue to do that. That's because what other people have been taught to do, but you really need to know that it's wrong. And it isn't just me who says it's wrong. I am not alone in this. DuPont Chemical says it's negative to positive. The only time you will have positive to negative flow is in either solutions or ionized gases, and that is a separate video. So thanks for listening. I hope I didn't upset anybody. This is reality. My background is military. I mentally still use electron flow, but I'll continue to, for semiconductor circuits, to use conventional flow. But I thought you needed to know this because you're going to run into things sooner or later that your conventional flow theory is not going to work. Because I found stuff in electroplating and stuff on the web where the authors tried to fit it to conventional flow and messed it up. So thanks for listening to the video. It'd be nice if you hit the like button. Please don't hit the hate button. Visit my website at www.bristolwatch.com. Have a great day.